So thank you all for staying. This is either the after-dinner talk or the after-dinner entertainment. I learned a long time ago when I was teaching at Clemson that I really only had control over at least one person in the room having fun, and if it had to be me, so be it. So I will try to. So I don't know, and Chelren can attest to this, the actual talk title looks eerily similar to what we started with this morning, where we were preparing the nurse community for next generation architectures. And here we're preparing a next generation of computational scientists for parallel thinking. And neither of us knew that the other's talk was going to be so titled, but this idea of preparing for the future. The subtitle of this is Beyond PowerPointlessness. So this is not a PowerPoint, it is a link. If you'd rather follow it along, we'll make sure you all get the link. It's all out there. So in terms of the general opportunities here, we'll just make sure that you get at least a little bit of sense. This is another trivia question. Through show of hands, how many people have heard of Shodor before? Not everybody, okay? Okay, another show of hands. How many people know where the name Shodor comes from? Not nearly as many. So I'm going to show you the power of inquiry-based learning by telling you a story with the expectation that if you pay attention, you'll be able to at least infer the origin of the name Shodor. When I was a young assistant professor of physics at Clemson University, a young man who needed me to sign a form so he could get a ROTC scholarship came to the physics office in such a tizzy because he needed me to sign the form by 4 p.m., but he could not remember my name. So he could not look on the directory what my office was, and he could not find me. So he says to the secretary, "All I remember is that he's short and kind of dorky looking." How many people think they know where the name Shodor comes from? And that's a true story. It's not the reason we used the name, because the lawyer in the incorporation meeting said we could not incorporate if the name was misleading or offensive. So he looks it up in the Oxford English Dictionary, and it turns out it's the name of one of the 3 steps in making gold leaf. You have to start with gold. It can't be dirt, it can't be gravel, it can't be wood. It has to be gold, and it has to be very pure gold. But to turn it into gold leaf so that it'll go farther, you have to beat on it and beat on it and beat on it. The name of that hammer is called a Shodor. And if you beat on it and beat on it and beat on it, what's the point at the end of the day if all the gold sticks to the hammer? So the idea is that there were several of us around the country who had ideas about changing the curriculum by introducing modeling and simulation. But we had to get it into the classroom. We had to beat on that curriculum until it fit, until it got into where it needed to go. And what would be the point if all we did was have, a really nice hammer? We wanted to get the stuff into the classroom. So that's where Shodor has come from. Some of you may or may not have heard of us in any particular way, but if you went to your favorite browser and typed in petascale education, oh, that didn't work. It never used somebody else's computer to do a talk that, okay, so this is done. So we're going to get rid of this and just go up here. Do we need to set up the, no, we can't possibly. Huh? We'll go back here. Petascale, if I can spell it, education. So it turns out that virtually every link on the first page of links that comes back is something about the Petascale, the Blue Waters internship program, and every link that's linked to it so that people know about what this kind of stuff is. We often talk about being womb to tomb. If you came over here and said, I'm interested in helping my kids understand adding, subtracting, multiplying, and dividing, and you say, well, is there anything on the net that I could test my kids with? And you say, well, we do have some things that have to do with adding, subtracting, multiplying, and dividing, and a lot of other things. If you're teaching environmental science, you might come up and say, well, what I'd really like to find is something that would give me a way of interactively studying rabbits and wolves. And so if you sort of go through this thing, is lots of people run into us on the net every day and have no idea who we are. And we don't care. There's over 5 million web views, not hits, web views a month of the materials that we've created to bring modeling and simulation into the classroom from, as I said, our range is womb to tomb, right? High chair to rocking chair, right? K to gray, whatever the range is that you want to talk about. And it's important because as we're going through these things, it's been an evolution. In the early 90s, to do what we're now doing on Macs and PCs, you needed a computer capable of doing 50 to 100 million operations a second. That was called a cray. Now, anybody can do 1 billion operations a second, and it's getting slower and slower as you get more and more cores, and each core can do less and less, right? So there is a problem of what's coming on, so we have to think about, you know, where all of this is going. All right, so we'll talk a little bit about this to sort of get you in the mood. Let's see if they'll turn the sound up on this. This is a song called Blue Waters is Wide.
Blue waters is wide. I can now combine the stacks of the rise. My hoops will fly. Give me a call that will decompose on many cores within the eye. There is a node runs for channel C. She's loaded deep with memory, and with each core, some local cache. I'll address it all universally.
In fact, if you want, we have an entire karaoke page that would, depending on time, we may get back to some of that. So let's talk a little bit about computational science education, and we have to do this with 2 breathing modes. One is computational science education, which is teaching the content of chemistry, biology, physics, geology, economics with interactive models and simulations. We're not necessarily teaching coding. It's one of my great peeves is, oh, we should have everybody learn coding. My question is, coding what? Oh, we're going to teach them coding. I understand that, but coding what? Well, you know, just coding. There's a tremendous amount of computing which doesn't involve coding. It requires an understanding of the computing. Many of my friends that are chemists don't code, but they run Gaussian, and they know what it does, and they know how to tell if it's working. A number of my friends run community codes. That's not necessarily our community. Did you see the slide this morning? There were 7,000 users for NERSC. How many projects? 750. How many codes? 750. So those folks need to know how to code because they're not just using somebody else's code. They are the generators of that actual material itself. So computational science education is a big part of computing, and it's a big way that people get into computing and recognize its value. But it's also important that we have computational science education, which is teaching people how to write the code and how to do verification and validation. How do you know if it's right? Right? So you have this big code that's doing it. One of the things that concerns me, and I'll talk to some of you individually later, is that we have a lot of people doing Monte Carlo in parallel, and they can't tell you anything about the random number generator. What did they use? Oh, I got something out of recipes. Really? Well, I just used a different seed on every node. Really? We need to do some things at this level, because if we're going to base the science and the learning of what we're doing on a code, and that code is not necessarily going to be reproducible, especially if it takes several million node hours to run. Now, someone else isn't going to run the same code just to check your work. We ought to have some reason to believe that what you're doing is right, and it comes in there. That means not just eureka, but it's actually research and discovery. Right? So it's not just the eureka, it's saknu and aravno, which are the search and the research parts of the learning that's going on there. Okay, let me make sure I hit the left button. So the ideas of what we've been doing for many years has been focused more on computational thinking and getting the dynamic, visual, interactive aspects of computation into somebody's classroom and into learning. One of the first things we did was try to kill off the big lie. And when we first wrote this, it was actually written with one of the earliest versions of a browser connected to a secret file on NCSA's Cray, where we were running an HTTP server on the Cray. And Larry Smarr never found out. But what we were doing was we wanted to kill off the big lie of the American math textbook, which on page 42 has a graph, and underneath the graph is an equation, and underneath the equation is written the most false words you'll ever read, as you can see from the graph. And when you stare at this static thing in there, and you say to yourself, I don't see that from the graph. So we created things that basically will run anywhere on anything, I hope. Apparently I'm clicking things that I didn't realize. Again, don't ever give a talk with somebody else's computer. So suppose you had a function that looked like it had bumps. And the real question is, you wanted to understand what changes the size of the bumps, what changes the number of bumps, what changes where the bumps start and stop, and what changes the average value around which the bumps are bumping. And as you can see from the graph, if you parameterize the function in a particular way, that you can separate those functionalities to get separate scaling in x, y, and shifts in x and y, and you can do that for any reasonable function. And you can type in your own function. You can, if you don't know what the functions are, you can take a picture of a function and say, oh, I want to do that one. But the idea is it's dynamic, it's visual, and it's interactive. Part of the story of tonight is we've got to learn to live with batch. One of the things we have trouble with is we get a lot of programs for middle school and high school and even undergraduates which are dynamic, visual, and interactive. And they really get excited about computing. And then we get them a count on blue waters. And then it's batch. So the question is, how do we maintain that interest even in such an irksome environment? A lot of the things that we've been able to do, this was 18 months of my PhD thesis to figure out how to take a set of charges and find the ground state energy using a classical Monte Carlo program. And as you can see, in JavaScript, in a browser, we can do it faster than 18 months, right? And we can find the ground state particular system that's going on there, and if we wanted to, we could then calculate the electrostatic potential at every point, and then using one or more of Donna Cox's palettes, we could come up here and say, okay, what if we decided to color that a little bit differently? how could we really understand the charge configuration, the electrostatic potentials, and then the electric fields that are coming out. And it's dynamic, it's visual, it's interactive. Now you say, okay, we want to do this with hundreds of thousands of particles. How are you going to run that? Batch. And you're not going to see it as it happens, and you may not get the same insight. And so we have to ask ourselves, how is that going to affect how students learn how to compute? And ask the question, how do you know if it's right? They don't see it. They have to imagine what it might be, having never really done it. So what we're doing is building a kind of launch ramp where we do the things that you can do with smaller systems, so you understand what you're trying to get to once you scale the thing up. And that's, again, starting to be more and more important. So if we can get to the next. So now let's change this to parallel thinking. I know in the old Far Side there used to be the bookshelf of hell, and it said rate problems, more rate problems, even more rate problems. So let's see if we can have a collective sense of the mob. If one painter can paint one house in one day, how many houses can 7 painters paint in a week? Right? So when I count 3, shout out your answer. 1, 2, 3. 49. Do you work 7 days a week? Well, actually, most people in this room probably do. But there's a fuzzy word in there, which is week. And that will affect things. But let's talk about the real world. What if you only had one paintbrush? What if you had 7 paintbrushes but only 1 can of paint? What if the houses to be painted were between 300 and 500 miles apart? What if you could get all the paint you wanted, the houses were close together, but you could only get the paint Tuesday mornings at 9:30, and they'll only sell you 2 buckets at a time? And so when you start looking at resource allocation, network latency, distributed memory, distributed resource, distributed processes, even if one painter can paint one house in one day, it's not clear that parallelism is going to necessarily benefit you depending upon the other constraints of the problem. It doesn't just scale. And one of the things that we've seen is that not everybody, but many people teaching parallelism tell you that as you increase the number of processors, the time to the solution goes down. And they forget to add the fact that you got to talk to those processors. And the amount of data that you have to transfer goes up. And it's the sum of the work and the communication that gives you your time to science. And the sum of those two typically has a minimum, and that minimum is usually not a very big number for n. And one of the things that we've been trying to teach people is to characterize the kind of work they're doing in terms of what kind of parallelism is going to help them. More processors on one problem, or several processors on a problem, but several copies of that problem running through the system. That's not something that people expect when they first get into the parallel system. So the world itself is parallel, and our thinking needs to be parallel, or at least it should be. I mentioned in the morning session that galaxies do not label themselves 1 through n and sum their pair potentials I less than j. That's just not how it works. It's an all-body problem. But what we've done is linearize or serialize the problem and then try to parallelize a serial algorithm. When in fact they're probably not 2-body potentials anyway, they're n-body. So the question is, what's the science involved, and can a parallel computer compute a parallel system in a better way? Right? So there are things like this that we're trying to get across to students, that what we really need to do is think about the science and where's the parallelism in the way it works, and use that to inspire us to find architectures or learn about architectures and see which ones match up to what kinds of problems. Because not all parallelism solves all problems with an equal distribution. But there are things you can think about as you're kind of going through there. Now, we've been doing this for a while, and there are ways to stimulate parallel thinking. And some of them can be incorporated in lots of different ways. Years ago, I think it was 95, there was a meeting at University of New Mexico. Frank Gilfeather, does that name sound familiar to anybody? Had a meeting on frontiers of supercomputing and industrial applications. And somebody asked this industrial panel, what do you expect of our graduating students? And immediately, the fellow from Boeing said, we want them to know 2 languages and 2 operating systems. And the fellow who was asking the question happened to be a Unix bigot, and he said, well, and which language and operating system would that be? And the fellow from Boeing says, we don't care. What we want students to know is there's more than one way to solve a problem. And we have students that come in claiming they know Unix. No, they don't. They know the C shell, or they know the Bourne shell, or they know the T shell, or they know Bash, or they know something. And then they spend their first 6 months working for us trying to customize their profile so that all the commands that they had learned when they were an undergraduate still work the way, so they don't have to learn anything new, right? But it turns out that lots of languages help, because not every problem lends itself to the same types of solutions and different languages. I'll tell you another story. This came from Mal Kalos, and I heard him tell it so many times, I think I might have even been there. We used to go to lunch every once in a while at the 2nd Avenue Deli, and he would at least tell the story that one time, every time he'd go there, the owner would always come over and talk to him because they were old buddies. And one time while the owner was talking to us, the cook came out from the kitchen, and he was an impeccably dressed Chinese cook. And he said to the owner of the place, Har Bilibos, die grins trok is spät. And the owner said, Azoi, mir verdienen allemens kleinere salads. And then the cook said, große Gedanke, boss, große Gedanke. Right? And so the guy goes back to the kitchen, and Mal Kalos said, where did you find a Chinese cook that speaks perfect Yiddish? And the boss says, shh, he thinks it's English. There's a certain point where what I really believe this is the case for a lot of things that we could be doing, where we don't have to teach hello world when you're teaching coding. We can start with the assumption that the coding they're going to do is in parallel. We don't have to start with a blank sheet and have them type. We can give them code that works, and they can see what it looks like in parallel. I've often said I haven't had an original idea in 30 years, and when I can show evidence of that, I'm very happy. 30 years ago, Nora Sabelli and I had a proposal to NSF to establish the National Repository of Exemplary Parallel Code. And the idea was to take the architecture, algorithm, application axes and find really good examples of how does N-body run on a Cray, how does it run on a CDC, how does it run on an Alexi, how does it run on some other system, and then do the same for other problems and other algorithms. What are different ways of solving N-body? Brute force, fast multipole, etc. And they gave us a planning grant, and at the end of it, a number of the advisors said, this will never work because nobody will share their code. Right? Academics are the worst. They will not give you their code. You can't get exemplary code in a national repository. Right? A few years later, the National Science Digital Library started. We were one of the groups that created what's called the Computational Science Education Reference Desk. In 2007, the proposal for Blue Waters went in, and we argued there needed to be an undergraduate component that involved faculty development, materials development, and student development. And the materials that we developed have turned out to be exemplary in showing people how to run on different parallel systems. Why, when a machine was going to take 5 years to be built, did we think we needed to have an education program? Well, because most of the people running on that machine, we figured 5 years once the grant was funded, once the machine turned on, would be first-year graduate students. And at the beginning of that process, they were still high school seniors who were smarting from either neither being asked nor being accepted to go to prom, right? So when you take high school seniors and you say, 5 years from now you'll be a first-year graduate student, how can we prepare you to be running on one of the world's fastest academic supercomputers? If you don't use that time well, we won't have anybody that'll run on it, except the people that wrote the proposal, and a couple maybe of their postdocs or things that are coming on there. So one of the things that we've done is to explore a parallel first approach, where if you're going to teach programming, why not teach it from a parallel standpoint? People say, oh, we have too much stuff we have to cover in the undergraduate CS curriculum. Well, I have a model that I like to use for that. Does anybody know what this is? It's an ashtray. Where did I get this ashtray? From an airplane. What kind of an ashtray is it? It's a no smoking ashtray. And by the way, there's a very sharp edge here, and this is already on the plane. So if you don't want to get caught going through security, just wait till you get on the plane, go to the restroom, and get your blade. If you were so inclined, but that's a different story. But the point is, there's lots of stuff in the undergraduate CS curriculum that is there because somebody says it's always been there. Why are we teaching it this way? Because that's the way we've always taught it. But you don't have to do it. Because there's a regulation that says the bathroom has to have an ashtray that will safely allow you to put out a cigarette if you illegally smoke when you're told not to. So you have one curriculum committee that says this has to be here, and you have the real world that says, but we don't use that. And there's a lot of things that we want to put in the curriculum, and we have to find room for it. So if we look for the no smoking ashtrays in the curriculum, there'll be plenty of time to do all kinds of things with parallelism. I will tell you that one of the problems is, at the undergraduate level, there are very, very few problems that require high-performance computing. And as a result, the level of effort to get into high-performance computing for the sole purpose of teaching high-performance computing, if it's not really teaching chemistry, biology, physics, etc., is a hard sell, especially at liberal arts colleges that want to be doing these things. So it is kind of a tough issue and a tough sell for things. One of the ways that we get people to think about parallelism is to point out, we educe. Education comes from the verb educe, to pull out of people. And we pull out their memories. How many people in their earliest days of elementary school ever took a short answer or true-false test that after the test the teacher had you exchange papers? And then they would read the answer and everybody would mark it? Single instruction, multiple data. That's what that is. And when you're teaching single instruction, multiple data, and people are having trouble figuring out, well, what is that? You could remind them, because they've already done that before. I mean, parallel first. When I was growing up, they were starting a band program in Northern Virginia. And my father, who was working for the government, not making all that much money, having 6 kids, wanted to find a way to keep us from wanting to be in the band. And the way he did that was requiring us to take 2 years of piano lessons. Thinking that, why would we want to do that? And having not done that, he wouldn't have to pay for a band instrument. But the 6 of us, individually over several years, did take 2 years of piano. And we learned to use all of our fingers playing different things in chords and progressions. And we used Michael Aaron's series, and we went through all the different books, and we learned all this stuff. And we learned what a note was and what a scale was. And then when we got to band, we only had to play one note at a time. We had already been doing parallel piano, and now we only had to do one note at a time. Right? And so the 6 Panoffs who ended up being first chair in flute, tuba, percussion, trumpet, French horn, and trombone, why? Because everyone else couldn't read music and they were trying to learn how to play their instrument. And all we had to do was figure out how to make a noise out of this thing. So parallel first has evidence of effectiveness of things that are going on. When I was in the Boy Scouts, we started a program called Better Scouting through Mathematical Analysis. So suppose you were trying to learn how to make a rope ladder, and they taught you. You basically take a part of the rope, put it over another part of the rope, and pull it in, and now you have 2 links on the rope ladder, then you have 3 links on the rope ladder, then you have 4 links on the rope ladder, and then you say to yourself, okay, what is the mathematical model of what I just did? So you can say to yourself, well, let's think about it. If you had all of the things in memory, you could fetch A, fetch B, do the division, A over B, store the result. Fetch A, fetch C, do the division, store the result. Fetch A, fetch D, do the division, store the result. And of course, each time you add it to the previous result. And then when you're done, you say fetch A, fetch E, do the division, store the result. And there's not only a rope ladder, but an algorithm. Now, if you stare at A over B plus A over C plus A over D plus A over E, what's the same in every term? A. So what can you do to it to simplify the expression? Give you a clue. Starts with an F and rhymes with actor it out. So what are you left with? 1 over B, see here's B, and I invert it. 1 over B plus 1 over C plus 1 over D plus 1 over E, and if you multiply it all by A, that's a vector pipeline. Right? That's an accelerator, right? That's the concept of, can you see that if you did it a different way, it could be faster, right? But it's those kinds of things where we're constantly going in and trying to find examples of what kids are already familiar with and put it in the language and vocabulary that parallel thinking is going to ask them to kind of go a little bit deeper and a little bit higher there. Single instruction, multiple data, sheepshank. Start with the outside loops, don't end with them. Bend the loops, do the tucks, do the pulls, do the tugs. And you can use different ways of, but you have to look at it and say, do I have to do it the way they've always told me to do it? Because it isn't necessarily going to be as fast, and it may need to do it, look at it more than one way. So when you're going through here, look at multiple paths to solution, because some of them are going to parallelize better than others, but not all of them. We emphasize modeling, where you run the model, modify the model, and then if you need to, write a model. But most of science, at least when I was in grad school, I wrote very little original code as a percentage of my PhD thesis code. I inherited the code that the last 6 persons had gotten PhDs with, and each one of them had made it a little bit better. The last chapter of my thesis I actually got by going to a different institution. Called up Mal Kalos at NYU and went and visited, where's Dave Sepperly? He was in here somewhere. So Dave, and it was Mike Lee and Kevin Schmidt, and went up there and learned how to do Monte Carlo. They said, I said, could you run this calculation for me? They said, no, but we'll show you how to run it. Right? And they gave me a copy of a Metropolis Quantum Monte Carlo code, and they were doing helium and I was doing deuterium, and I ended up with a thesis out of it. I wrote very little of that code, but I knew how to read the code, and I knew what it was doing, and I knew the physics behind it. And then I learned more and more of it as I ran the code more and more. And then they gave us 100 minutes a month on the Cray at Livermore. 100 minutes a month. And we could do more in that 100 minutes than we could run for the whole month on the VAXs that we had at NYU at the time. But it was a matter of being able to use other people's codes. There are now tremendous numbers of modules that were funded by Blue Waters that, as you've seen before, are really, quite extensively used by the community. And there's also ones run by a project called Little Fee, which involves a little appliance that has 6 boards. Each board has multiple processors plus accelerators, and you can learn all you need to learn about MPI, OpenMP, OpenACC, CUDA, and then the curriculum that goes with it allows people to go into existing working examples and not start with a blank sheet and teach them Hello World. By the way, there is an example if you want to, which is Hello World. But you don't have to start there, right? And again, this is the kind of things that if you came up here and just said, what if you typed in the words CUDA matrix? Well, if you do that, what you get is the module paid for by Blue Waters to show people how to do that with a complete set of curriculum that goes with it. Right? Right? If you came up here and I think, I'm just making stuff up here. So, N body module. I forget what. All right, so there's an entire set of things in high-performance computing of how to set up the N-body and how to do it on different architectures and what's involved and what's the difference between brute force and fast multipole. Anybody remember the problem with fast multipole? If you don't have 10,000 particles, it's not faster, right? So unless you're really willing to do something big and have a computer that's big enough to get it in reasonable time, a better algorithm isn't necessarily a faster algorithm for the same problem that was small, dynamic, visual, and interactive. Right? So these are the lessons that we're kind of learning as we're going through. Now, none of us are doing this alone. So the question is, how is Blue Waters involved in the community? So here's a cascading style sheet that you can figure out. It really starts with teaching and the professors in their research and teaching. And I'm not necessarily going to click on all these, but if you were to click on the professors, you would see that Blue Waters is funding a substantial number of faculty, a lot of them, if not most of them, at the University of Illinois. Is that right for the professors? The Blue Waters professors are Illinois faculty. And they're not only doing the research and they get a substantial part of the machine, they're bringing this into their classroom and getting their own students to be learning how to do that. We also have the graduate fellows that you saw up here, a very select program, and they get a chunk of money, more than I got as an assistant professor, but I'm not jealous. And the important thing is I'm not bitter, okay? But they also get a gazillion node hours, and they get help, and they get one-on-one consulting, right? Don't they get a point of contact at NCSA? And they get people that will help them be successful, right? And they get a certain amount of independence because they're bringing in their own funding to really work on their research, and it's been a very successful program. We also have education allocations for both undergraduate and even some high schools, where 1% of the machine was set aside originally by Tom Dunning for education allocations. And the main thing you have to prove if you get an education allocation is you're not sneakily trying to do research. You're trying to teach people how to do research, but you're not really trying to bypass the normal allocation procedure. So there's the education. We also have the Blue Waters interns, the undergraduate interns. And this is a program which has been running since really the beginning of even before we had a Blue Waters machine, and we were running on vaporware, for several years. And then, we would run on Oklahoma's machine or Texas's machine. And then finally, when Blue Waters came around, we really could do a tremendous amount of things that are going on. And if you go through, you'll see one of the things that's very impressive is the degree to which a diverse group of students have been selected without selecting for diversity. It is an interesting program because different from others, we're not picking the best people. In fact, if somebody writes a recommendation that says, oh, my kid is the universe gift to parallel computing and he already knows this and then he doesn't need to be an intern. At least not paid for with this money. So we look for people that have the most potential to learn and grow by learning how to be a researcher and an intern in a highly productive, massively parallel system. So it's the creation of quality, not the rewarding of it, that's the internship program. We also we developed a 2-week institute that's the equivalent of a semester and a half of graduate education. Again, the whole curriculum is online if people want to do it, and people have been doing it. We have a number of undergraduate colleges that take the curriculum of the institute, which is basically 6 hours a day plus a 3-hour lab every day, right, Claire? Except we give them Friday night off, okay? And if they come back the next Monday, we do it for another week. 6 hours a day plus a 3-hour lab. And when you're done, you've essentially had, a 90-hour experience of high-performance computing. And on day one, they're running code on blue waters. They're running a galaxy simulation, understanding the rate of rotation of an n-body system, and how in one case you get a galactic cluster, and in other cases you get disks, but it's real code running on a real computer. We try to stay away from hello world, right? That institute is successful enough, and we have extra room so that we take the Exceed students who are going to be working in different things, and we bring them to the same institute. So we have these partnerships between Blue Waters and Exceed in which things that we're doing for the community can be used by the community. And there's a particular new part of Exceed 2.0, which I'd like to point out under student engagement, which is called Empower. And some of you, again, we're not looking for students who are already the best, but if you have a student who wants to learn HPC and you're willing to mentor them, we do not have a penny for you, but we'll pay for your student. And we'll pay them if they're a learner, an apprentice, or an intern, depending on where they are, and they get more as they kind of move up the food chain. And that program is called Empower. If you go down all these different pieces of things that are here, and you can find, oops, that's the wrong one. I have to click Empower. So there's an application procedure. The students can do it a semester at a time or for the summer. It's not like the Blue Waters internship, which is a year commitment. You can sort of test the waters and see if it's what you want to do, and then come back for another semester or for a summer and continue doing it, kind of moving up the computational food chain. So that's an important part of what's new about the things that are going on. And then we have the things that we're doing in North Carolina. At Shodor, we have elementary, middle, and high school kids that come in, and we teach them computing, modeling, simulation, web design, graphics, parallel computing, because they don't know any computing, so why not start with parallel computing, right? Put them on Littlefeet, put them on a Blue Waters account, let them see what it's like to do these things, satisfy their need for immediacy with things that run on a Mac or a PC, and then gradually wean them off as they get excited about running batch on the country's fastest supercomputer. Right? And we have, a fairly successful group of these students, and one of the things, again, that's fairly impressive to me anyway, is we don't select for diversity, but by picking students who want to learn, we end up with quite a substantial group. And if you went to the Shodor website, you could look at their work. You don't have to take my word for it. Here's an 8th grader from Smith Middle School, 8th grader, right? And then she's got her own portfolio, she's got her own blog, she's got things that she's done, she's got a parallel notebook talking about all the things that she's learned while she was learning things at Shodor, right? And she's got something to show for the level of effort. That's an intensive program, 3 Saturdays a month, 6 weeks in the summer, right? And if they have a project and they don't get it right, they have to do it over. Right? They learn about verification and validation. It's a big piece of what we're doing there. So what are some of the things that we've learned? Focus on the science, because that's what people can imagine and see in the world, or imagine seeing. You got rabbits and wolves. All the rabbits don't sit around until one rabbit hops, and then all the wolves sit around until one rabbit steps, and then all the rabbits sit around until another rabbit hops. Right? It's a parallel system. It's an n-body problem. So they learn to think like that in different types of codes that are going on. So learning to keep going back to the science. And then we have to model what we're teaching. We have to be insistent that what we're thinking about is the science and not just how fast can we get this code to run. How do you know if it's right? There's a lot, I don't know if you remember the old Cray optimizing compiler that would just optimize the heck out of something and get you a completely wrong answer, but really fast. You know? I mean, that was just amazing. So those are things that we're doing. Learning to think about what you're doing and not just accept the default. I like to say it's not a coincidence that 5/7 of default is fault. Right? I'm going to use the default compiler. I'm going to use the default initialization. I'm going to use the default, whatever it is. And then the excitement for science is something that we really, really have to pay attention to and not let your students get discouraged. Excitement for science can help, what I say, overcome the annoyance of batch. Anybody know what TT therapy is? There. It's not really that bad. You'll get used to it. And besides, while the code's running, you can think about how would you know if it's right when the answer comes back? What are you looking for? How will you visualize the data? Right? You know, so you're not frozen in front of the computer as it's running, having to be the observer. Now you have to think about what's the data going to look like and how are you going to visualize it when it comes back. But batch could be an opportunity to free up your time to be thinking. Sometimes more time than, it could be days. It depends on how things work. And then in a certain way, computation and communication is the definition in many ways operationally of big data. If you spend more time moving the data than using it, that's big data. Right? So, I mean, you have to have a sense of, it's a relative term for things. I mean, Shodor started years ago, as people were coming up to things going back and sort of coming back through all these different things. And one of the big data, this was 1994, November of 94, they took out a 21 centimeter tumor pretending to be my left kidney and then showed me data of life expectancy in years versus size of tumor. And what they had was up to 10 centimeters. And so we tell those people 6 months to a year. We have no idea we'll tell you, I know, how about 3 to 6 months? What do you think? So I was talking to somebody who was really upset that I had missed a budget meeting while I was in surgery. And I thought to myself, if I've only got 6 months, why would I want to spend it with you? And went off and we've had fun for several 6 months over. But this is a piece of what we're doing and how we're doing. I hope you've gotten a sense of that the education program is a little bit more than just occasionally once a year seeing some people. And I want to thank you and my students and Aaron's students and Jennifer's students. I want to thank you for all the attention and time that you've given us and hope that we've taught you something about getting students really excited and interested about parallel computing. Thank you. Yeah. Yeah.
So are there any questions for Bob or any comments on what he was sharing with us? I think it's a fantastic talk, particularly after dinner. But are there any things you want to ask? This is a person that has tremendous vision as well as insight into what we do here. So, sure.
I'm curious what the parallels between what support you give your staff are with the support that you expect your sort of staff on the ground working with students to give their students. What are the parallels between those two levels of support?
We're a very flat organization in the sense that people are pretty much in charge of the things that they're doing. And the programs we have for elementary, middle, or high school kids, one of the things we used to say is we only hire mentors, right? So everybody at Shodor is being mentored and they themselves are mentoring students. It's our favorite approach. We were thinking of getting a bumper sticker that said, "We'd rather be mentoring," as we sort of go through there. But it is an important part. We've have a very simple structure. It's a nonprofit. We try to get the money to be successful and keep people busy working with kids, because that's what they appear to enjoy doing most of the time. Almost everybody that's worked at Shodor, and some of them have gone off to do great things for much bigger companies that pay them to be outstanding programmers, or the biggest pipeline we've had is to people that work for places like SAS, and they do quality assurance because they really understand verification and validation. That's a big part. So we have kind of a self-growth effort of things that are going on there for the staff, and it's not a very big staff. And then, for them to work with the students themselves, it's something that people have actually come back from other job opportunities to work again at Shodor. So it's something we're trying to continue. We only have 3 rules at Shodor, but they're ingrained in Shodor staff so strongly that I can say half of the rule and they'll shout out the other half. Those who work raises become effective. And it's always better for you to tell me. That's it. 23 years, we're still going.
Excellent. Blue Water staff, have you been listening?
Yeah, so I'd love to say that wonderful ideas are infectious and will spread on their own, but this is something that education programs at a much larger scale can benefit from, a lot of these ideas you've developed. So what sort of actions is Shodor trying to take for that?
Well, we make everything accessible, so it's discoverable. We also do a lot of faculty workshops. And we try to work with faculty whose students are going to be K-12 teachers. We do some K-12 workshops, but not nearly as many as we try to work with faculty whose students are going to be teachers. And then we also do workshops at a lot of the CCSC. Anybody familiar with the Consortium for Computational Science in Colleges? We do workshops for those groups there. We run our own, mostly funded by Exceed these days. For several years, in the first thing, we actually were trying to get faculty to understand parallel computing, so Blue Water's even funded some of those workshops. And now we're trying to find ways to scale those up through synchronous and asynchronous use of technology. Right. But it is a hard scale, and most of the growth has been viral. It hasn't been, massive epidemiology type scaling. It's been a little bit gradually pushing back the boundaries of darkness. So, but it is a big effort, and we'd love to, keep doing it.
So I was wondering, have you seen the diverse and marginalized student populations from these undergrad and younger mentoring programs actually go on to science careers using HPC?
Yes. And in fact, we've seen some of the kids that come over from our elementary and middle school programs go into math and science when all they were really looking for was a summer workshop that happened to use computers to do something. So we've seen a fairly broad success in people going on to careers in math and science, and that seems to be very much there. Right. And a lot of the, not a lot, I mean, we're not that big a staff, but many of the staff at Shodor had actually started out as interns, and over time we've had actually staff that started out as high school kids, went to college, worked for us during the summer, went and worked for a job for a couple years, came back, worked at Shodor for a couple years, went to grad school, so it is kind of a growing cycle of things.
I think it's absolutely amazing what you're doing with middle school and high school students. But when we tell, in my experience, classes of grad students that they're going to write their first hard sphere Monte Carlo code or something like that, you get this deer in the headlights look. So what sort of stuff from your experience is really good to get people engaged when they're later along in their careers and haven't really been exposed to HPC?
Give them good code that makes a difference in their research life, and then help them understand what it does and how it does it, right? They learn how to modify that code. They learn how to understand it. They don't have to write their first code with the deer in the headlights look. They get a code that they already know works and has been the basis of a number of published papers. And they become successful by running something that works. My staff and others who've been in my workshops will know the one thing I cannot stand about certain ways of teaching computer science is on the test it says, here's some code that's wrong. Fix it. Without having any idea really what it's supposed to do. But that's a different story. But the idea that somehow, or here's some lines, fill in the missing lines, rather than here's something that works. Learn from it. You could learn a lot by working with stuff that actually works. Now, it didn't used to be that way. I mean, 100 years ago, if you wanted to drive a car, you had to make it. Or you would find one that was broken and you'd had to learn how to fix it. And even if you got it new, you had to learn how to fix it because it was constantly, I mean, that's where all these names came from, like Ford, fix or repair daily. But again, you have these things. But to be successful, let them be successful. Don't start them off where you kind of give them a leap they have to jump over in order to get into your little fraternity. We want to grow the number of people that are doing this, not keep it constricted. Personal opinion.
Any other questions? Shout.
For a couple $100, you can buy a GPU now that has more parallelism internally than a supercomputer 15 years ago.
Yep.
Has that changed how you teach parallel thinking?
It's changed how we're trying to teach things. I mean, many of these computers come with a GPU in it, but don't really come with the software needed to access it. I mean, they just announced yesterday a 16-core, 32-thread chip that's going to be powering somebody's laptop down the road. But, unless you have 16 different things that you're trying to do, where one of the cores runs your email, one of the cores runs your music, one of the cores runs Excel, one of the cores runs Word, you're not going to get much benefit out of having 16 cores. So once we have virtually every machine that's being bought or sold is a parallel system anyway, there are opportunities to do that. And one of the projects that came out of the little fee is called BCCD, which is a bootable cluster CD. That was the original name for it. I forget what it stands for now. But the key thing is you can easily install that software as sort of a second operating system, even without partitioning your disk. And when you run it, you have full access to all the tools of MPI, OpenMP, OpenACC, CUDA, OpenCL, right? And you can have all of those things that are out there so that we can, take advantage. We don't even have to go buy a GPU. A lot of these already come with it. It's just normally you don't have access to it unless you buy a game that uses it, right? But you can with the right modeling environment. So I would recommend, is it bccd.net? Okay, just look it up. The software is there. The curriculum we showed you is there. There's a lot of stuff that's available. Yeah, absolutely. And I'd rather do that than a Raspberry Pi. Interesting, but it's not where the future's going.